Well, good afternoon, folks. Welcome to WNAGY, where we get together to discuss some outstanding problems. Let me go ahead and share our notes with you, and let's go ahead and wrap up this bad boy. At this point, we are looking at, let's see, uh, problem number 1, and this is from Unit 1.12. So the prompt reads like this. Which of the following functions is not continuous on the interval -infinity to infinity? So all real numbers. Now, we've already discussed earlier the functions that we are familiar with that are continuous everywhere. And I believe polynomials are in that group. And so these functions are, or this function f of x is continuous for all real numbers. Likewise, e to the negative x is continuous everywhere, so is the cosine, so their product will be continuous everywhere. Here we have a little bit more, I guess, closer scrutiny for the denominator, but again, e to the negative 2x is continuous everywhere. Adding 4 to that will keep it continuous. And more importantly, we should consider the fact that 4 plus e to the negative 2x is always going to be greater than 0. That's important because e to the negative 2x by itself is always greater than equal to, actually greater than 0. We have a horizontal asymptote at y equals 0. So consequently, there's no danger of the of h of x being undefined or discontinuous in over the set of real numbers. And so D, it looks like without any scrutiny, will be our function that is discontinuous somewhere. However, what we're going to do is actually explore the denominator. If the denominator is 0, then k of x will be undefined at that value of x. So let's see if we can factor the denominator. So x minus 4, and then of course x plus 2. And is this equal to 0 anywhere? Let's find out. X equals 4 and x equals negative 2. So indeed, function k of x is not continuous on the interval -infinity to infinity, so we found the appropriate answer. Let's take, so these are not nearly as hard as they seem. And so let's take a look at the problem number 2. It has 3 parts. And so which of the following functions are continuous on the interval -4 to 2? Well, let's take a look at it. We're looking for continuous on this interval. And number 1, f of x, looks like a troublesome expression. We know that x squared minus 4 would have to be greater than 0. That means that x squared would have to be greater than 4. And so we have some difficulty solving quadratic inequalities. I consequently encourage you to solve the equation x squared equals 4. We get x equals plus or minus 2. These are our critical numbers on our number line, and they subdivide the number line into 3 parts. Using test points, we're able to go ahead and determine where x squared minus 4 would be positive. What would be good test points to use? Potentially, let's see, 0 would be a good representative of that middle interval, perhaps -3 for the interval on the left, and 3 for the interval on the right. Again, we're attempting to assess the sign of x squared minus 4. When I plug in 0, this is negative. I don't think that would be a suitable domain for f of x, being that it's a natural log function. Let's go ahead and plug in 3. So 9 minus 4, yep, this is positive, that's good. And then of course, plugging in -3 into x squared minus 4, we end up with 9 minus 4, 5. That's positive as well. And of course, in this particular problem, we're really focusing on the interval -4 to 2. And I do believe that in this case, that would be part. This is an open, I guess, point. And so indeed, the interval, the open interval, -4 to 2, is going to be, and regrettably, Mr. Nagy has a typo there. I meant to put a -2 there. So let's go ahead and change that now on the fly. And so if the problem reads like that, in that case, indeed, I do believe that number one, f of x would be continuous on the open interval -4 to -2. Okay, let's investigate further. Let's see, number 2. So this was number 1. Okay, number 2, we have, let's see, g of x is equal to x plus 3 over x plus 3 and x minus 3. So let's see, we have problems at -3. The denominator would be equal to 0 at x equals plus or minus 3. And I believe that -3 is right in the middle of our open interval, -4 to -2. So consequently, a g of x is discontinuous on that interval. So let's go ahead and investigate h of x. Oh, well, I think that one was going to be an easy one. It's sort of a gift to us, I guess. X squared plus 9 is never 0. So consequently, this one is also, h of x is going to be continuous. So the true statements for continuity on the open interval -4 to -2 is 1 and 2. 1 and 2 are true. Okay. Let's go ahead, and again, this is pretty much all of these problems are discussing continuity either at a point or on an interval. And so let's take a look at, again, a reiteration of the definition of continuity here, but you're intimately familiar with this at this point. So let's go ahead and take a look at the two examples that are offered here. And as you can see, as we discussed earlier, the calculator problems are highlighted here as well as on the AP Classroom. And basically there's a calculator icon. And let's see what the question is. Let f be the function defined above where k is a constant. For what values of k is f continuous for all x? Okay, so if we look at this problem carefully, each part or partition taken one at a time, 3 plus cosine of x, that would be defined for all real numbers, and some constant k times x times the square root of x squared plus 1, again, would be defined for all real numbers. And here in this piecewise function, they are partitioned as follows. This is the definition on the interval where x is less than or equal to pi. And this, of course, is the definition down here when x is greater than pi. So in order for this function to be continuous, what we need to do is simply find the limit as x approaches, let's see, pi from the left. And then, of course, that would be for 3 plus 2 cosine of x. And this would have to equal the limit as x approaches pi from the right. And that would be for k of k times x times the square root of x squared plus 1. And then, of course, this would have to equal basically f of pi. If these conditions are met, in that case, this is a continuous function for all real numbers. And it is a calculator problem, mercifully. Okay. However, let's take a look at what we are looking for. Let's see. I think we can set this up as an equation, and we can't just go directly to the calculator, but what we can do is we can set this up as 3 plus 2 cosine of x equals k times x, let's see, the square root of x squared plus 1. And we can actually find these two limits that we've highlighted up here. I'm just underlining them. By direct substitution, since both functions are continuous, the 3 plus 2 cosine of x over the set of real numbers, as well as the k times x times the square root of x squared plus 1. And so direct substitution will allow us to solve for this. And at this point, we need to solve for k. So dividing by the x times radical x squared plus 1 on both sides gives us the following. We have k is equal to the ratio of 3 plus 2 cosine of x, all that over x times the square root of x squared plus 1. And we can use our calculator to evaluate this expression where at pi, because that is, let me see if I can highlight that, that is what we're looking for, f of pi. And so let's see what this value generates. We're going to switch over to the calculator, and let me see if I can share that. There we go. Here's the calculator. And at this point, I have already, for the sake of time, entered into y sub 2 right here, the expression for k. And so we'll come back to the home screen, so second quit. And on the home screen, we'll go ahead with the alpha trace key. We should be able to, we're using the second function. And that's the expression for k in terms of x. And so we'll evaluate that at pi. And let's see what we get. So entering this, I am getting basically 0.0965 as the value of that expression at pi. 0.97 rounded off, okay? So let's see, k is approximately 0.097 according to our computation. So that leads us to probably editing the answer choices here. But I think the key for our explorations here is to see how we could go ahead and solve this problem. So without any further ado, what I'll do is go to our last example, and this is similar to what we just did, but this is a non-calculator problem, and I'm not sure if I'm sharing the right screen with you. So let's come back here and make sure that the OneNote screen is being shared. So let's see. Here we are, okay? And so at this point, we are back to our OneNote, and we're looking at problem number 2 for unit 1.13. And we have a piecewise defined function with a literal constant a. And let f be the function defined above, where a is a constant. For what values of a, if any, is f continuous at x equals 4? Well, let's investigate. So for continuity, we know, of course, that f of 4 which in this case is going to be a squared minus 16, okay, would have to equal the limit of f of x. So the limit, let's see, as x approaches 4 from the left. So we have a squared minus x squared, and that gives you a squared minus 16. And so those two, of course, are equal. And additionally, we'd have to have limit as x approaches 4 from the right for a times x minus 10. And that would also have to equal a squared minus 16. Again, that definition of continuity at x equals 4 at that point. And what is this limit here? The right-hand limit is let's see, negative 6a. Okay, so that gives you the equation a squared minus 16 is equal to negative 6a. Again, we're applying the limit definition, the definition of continuity at a point. And folks, we do need to use the notation with appropriate limits, like you see here. This is essential in order to get credit. This is a calculus class. And then one thing that we tend to forget as students is also we need to make sure that we evaluate the function at that point. After all, the definition of continuity at a point is the limit as x approaches c for f of x is equal to f of c. Now, a little more to be said about this. This is what we're trying to show, but we need to use the name of our function and the actual numerical value of x, not just some generic c. If we use some generic c, in that case, that's a recipe, and that does not earn points on the AP test. But getting back to our problem at hand, what do we have here? We have okay, so this is a quadratic. Let's actually go ahead and solve this. A squared plus 6a minus 16 equals 0. We're back in our algebra days, and I believe we can factor this with relative ease. So a plus 8, and then we have, let's see, a minus 2 equals 0. What do we get? A is equal to negative 8, and a is equal to 2. So let's see. What are we trying to address? Let f be the function defined above where a is a constant. For what values of a, if any, is f continuous at x equals 4? Apparently, the definition of continuity of f of x will be met at x equals 4 with the following two values of a. A equals negative 8 and a equals 2. So consequently, the solution is C. That does conclude our investigation of outstanding problems in calculus for this afternoon. Hopefully you find this beneficial, and I look forward to seeing you in class very shortly I guess Thursday. Thank you.